Hello! This video, we are going to prove the following theorem. There is a one-to-one correspondence between the ordered pairs of positive integers and the positive integers. And to start out the proof, we're going to start out by defining a function which we will prove is a one-to-one correspondence between these two sets. So this is it. Now, before we get into the details of this proof, I would like to give a visualization of what this function looks like. Now, if you set the ordered pair 1, 1 into the function f, you're going to get an output value of 1. If you set the ordered pair 1, 2 into the function f, you're going to get an output value of 2. If you set the ordered pair 2, 1 into the function f, you're going to get an output value of 3. And check this out. This right here is the general pattern that the function f will follow. And yeah, it looks like we have a one-to-one correspondence between these two sets, right? It seems that no matter what ordered pair of positive integers we send into the function f, the output value will always be a positive integer. It also seems that f is going to reach every single positive integer, and no positive integer will be repeated. And yeah, now, before we get into formally writing any more of the details of the proof out, we're going to first figure out some of the preliminary results that we're going to use in our proof. And the first preliminary result is the following. For the sake of argument, consider the diagonal strip from 11 to 15. Notice that this is every single ordered pair of positive integers whose coordinates add to 6. And we can conclude that for every ordered pair of positive integers whose coordinates add to 6, the output value is always between f of 1, 5 and f of 5, 1. In other words, for every two positive integers I and j where I plus j is equal to 6, f of I, j lies between f of 1, 5 and f of 5, 1. And since I plus j is equal to 6, this means that 5 is equal to I plus j minus 1. And so this is another way of saying it. But it turns out it's true no matter what I plus j is. Right, in this scenario, we only investigated the diagonal strip from 11 to 15. The same result would hold if we instead investigated the diagonal strip from 7 to 10. It's just, instead of I plus j equals 6, we would have I plus j equals 5. And that's the idea. Turns out it doesn't matter what I plus j is. So, for every two positive integers I and j, this is true. That's the first preliminary result that we're going to prove. Now, here's the second preliminary result. Notice that f of 1, 1 is less than f of 1, 2, which is less than f of 1, 3, which is less than f of 1, 4, and so on. Also, f of 2, 1 is less than f of 1, 3, which is less than f of 1, 4, which is less than f of 1, 5, and so on. Also, f of 3, 1 is less than f of 1, 4, which is less than f of 1, 5, which is less than f of 1, 6, and so on and so forth. The general pattern here is, for every two positive integers m and n, if m is less than n, then f of n, 1 is less than f of 1, n. And this is our second preliminary result. Okay, so now let's dive into the details of the proof. Let's first prove the first preliminary result. So we're going to prove this. And notice, this is a reasonable claim because each of these three ordered pairs are ordered pairs of positive integers, as they should be because f is over the domain of ordered pairs of positive integers. Right? Given I and j are positive integers, we have that I plus j minus 1 is also a positive integer. Okay, now let's actually prove the claim. And we're trying to prove a statement about every two positive integers, so give me any two positive integers. I'll call them I and j. And so we're going to prove this in two parts. We're first going to prove this inequality, and then we're going to prove this inequality. Let's start out by proving this inequality. Now, what is this value? Well, to figure out what it is, we're going to use the formula, right? We're going to take everywhere we see an I and replace it with 1. Everywhere we see a j, replace it with I plus j minus 1. Right, so just like that. Now, if we simplify this first parentheses, you're going to get I plus j minus 1. If you simplify this second parentheses, you're going to get I plus j minus 2. However, since I is a positive integer, we know that 1 is less than or equal to I. And this is precisely what f of I comma j is equal to. So we have that this is less than or equal to this. So we have proven the first inequality. So now that we've proven the first inequality, we're going to prove the second inequality. Now, to compute this value, we are again going to use the formula, right? We're going to take everywhere we see an I and replace it with I plus j minus 1. We're going to take everywhere we see a j, replace it with 1. Now, if you simplify the first parentheses, you're going to get I plus j minus 1. If you simplify the second parentheses, you're going to get I plus j minus 2. Now, we know that since j is a positive integer, it follows that j minus 1 is greater than or equal to 0. So this is true, and I'm just going to get rid of the plus 0. So this is true. But really, this is the same thing as f of I comma j. So this is greater than or equal to this. So that proves the second inequality. Therefore, this is true. So we have proven the first preliminary result. So we've proven the first one. Now we want to prove the second one. But before we prove the second one, we have another claim that we're going to prove. That was good, right? And that is, for every two positive integers, m and n, if m is less than n, then n squared plus n is less than or equal to n squared minus n. And to prove this claim, let's first give ourselves an arbitrary positive integer n. And we're going to finish the proof of this claim by induction on n. So what we're going to do here is we're going to prove for all positive integers n greater than m, this is true. Let's first prove the base case. Now remember, in the base case, we're trying to prove that this is true in the case where n is the smallest positive integer greater than n. In other words, in the base case, we're trying to prove that this is true in the case where n is equal to m plus 1. So, let's start out by writing the right-hand side. Right, we're going to replace everywhere we see an n with m plus 1. If we expand out the first parentheses, you're going to get m squared plus 2m plus 1. Expanding this one out, you're going to get minus m minus 1. And this just simplifies down to m squared plus n. So what have we shown here? We've shown that this is equal to this, which implies that this is less than or equal to this. So what this means is we have proven that this is true in the case where n is equal to n plus 1. So this completes the base case. Now let's move on to the induction step. Now in the induction step, we give ourselves an arbitrary positive integer n greater than m, where this is true. And the whole goal of the induction step at this point is to show that this is also true for n plus 1. And to see how that comes together, check this out. If we expand out the first parentheses, we're going to get n squared plus 2n plus 1. If we expand out the second parentheses, we're going to get minus n minus 1. And this just simplifies down to n squared plus n. And since n is a positive integer, it follows that n is greater than the negative of n. And by our induction hypothesis, we know that n squared minus n is greater than or equal to m squared plus n. So what we've established here is that this is less than or equal to this. Which means we have proven that this is true if instead of n, we have n plus 1. And that was the whole goal of the induction step. So this completes the induction step. And therefore, this proves the claim. And now, we're going to prove the second preliminary result. And we're trying to prove a statement about every two positive integers, so give me any two positive integers. I'll call them m and n. And with these two positive integers m and n, we want to prove if this is true, then this is true. So let's suppose that m is less than n. And so our whole goal is to prove that this is true. And to see how that comes together, well, I'm going to start out by writing f of m comma 1. Now, applying the formula for f, we're going to take everywhere you see an I, replace it with m. Everywhere you see a j, replace it with 1. If we simplify this, we're going to get m times m minus 1 over 2 plus m. If we expand out the parentheses, we're going to get m squared minus m. And combining this all into a single fraction, we're going to get plus 2m over 2, which gives us a plus 2m in the overall fraction. And so as you can see, this would just simplify down to m squared plus m in the numerator. But since m and n are positive integers where m is less than n, we have that m squared plus m is less than or equal to n squared minus m. And notice that the numerator is the same thing as n times n minus 1. And notice that the numerator is the same thing as n plus 1 minus 1 times n plus 1 minus 2. And this entire thing is less than itself plus 1. And if you apply the formula of f, you replace everywhere you see an I with a 1, replace everywhere you see a j with an n, you have that f of 1 comma n is equal to this. Therefore, f of m comma 1 is less than f of 1 comma n, which is exactly what we wanted to prove. So this proves claim number 2. So now we're going to prove that f is a one-to-one correspondence between the ordered pairs of positive integers and the positive integers. In other words, we're showing that f is a bijection from the ordered pairs of positive integers to the positive integers. Now to start, we're going to show that f is a function from the ordered pairs of positive integers to the positive integers. Because currently, all we know is that f is a function over the domain of ordered pairs of positive integers. More precisely, we're going to prove that for every ordered pair of positive integers I comma j, we have that f of I comma j is an element of the positive integers. And since we're trying to prove a statement about every ordered pair of positive integers, give me an arbitrary ordered pair of positive integers. I'll call I comma j. From here, our whole goal is to deduce that f of I comma j is a positive integer. Now, let's immediately note that I is a positive integer and j is a positive integer. And to show that f of I comma j is a positive integer, we're going to divide it into two parts. We're going to show that f of I comma j is an integer and that f of I comma j is positive. Let's first show that f of I comma j is an integer. And to see how that comes together, well, since I is an integer and j is an integer, surely I plus j minus 1, I plus j minus 2, and the product of I plus j minus 1 and I plus j minus 2 are all integers. And for shorthand, I'm going to call the product of these two k. Now, since these two integers differ by exactly one increment, one of them must be even. And when we have a product of two integers where one of the integers is even, the product must be even. Therefore, k is even. But what does it mean for k to be even? Well, by definition, it means that there is some integer t such that k is equal to 2t. Now, if we compute f of I comma j, we have that f of I comma j is equal to k over 2 plus I. We know that k is equal to 2t. 2t over 2 is just t. And since t and I are both integers, it follows that t plus I must be an integer, so f of I comma j is an integer. So this shows that f of I comma j is an integer. All that's left to show now is that f of I comma j is positive. How can we do that? Well, since I is greater than 0 and j is greater than 0, it follows that I plus j minus 1 is also greater than 0, and I plus j minus 2 is greater than or equal to 0. Right, also has to do with the fact that we're dealing with integers. Now, the product of two numbers where one of them is greater than 0 and the other is greater than or equal to 0 is greater than or equal to 0. So really, the product of these two must be greater than or equal to 0. And since k is greater than or equal to 0 and k is equal to 2t, we must have that t is greater than or equal to 0. So, notice that t is greater than or equal to 0 and I is greater than 0. Well, when we add those two together, the resultant will be greater than 0. So really, f of I comma j is equal to t plus I, which is greater than 0. So what have we shown here? Well, we've shown that f of I comma j is an integer and f of I comma j is positive. Therefore, f of I comma j is a positive integer. So, wrapping this up, we started with an arbitrary ordered pair of positive integers and proved that the output value it yields to the function f is a positive integer. Which means we have proven precisely this statement, which amounts to proving that f is a function from the ordered pairs of positive integers to the positive integers. So we've shown that f is a function from the ordered pairs of positive integers to the positive integers. Now, all that's left to show is that f is a bijection from the ordered pairs of positive integers to the positive integers. And to do that, we're going to show that f is both injective and surjective. Let's start by showing that f is injective. Now, what does it mean for f to be injective? It means that for every two ordered pairs of positive integers, say I1 comma J1 and I2 comma J2, if those ordered pairs are different, then the output values they yield to the function f are different. Right? So that's what we want to prove. So give me any two ordered pairs of positive integers, I1, J1 and I2, J2. And from here, we want to show that if these two ordered pairs are distinct, then their output values they yield to the function f are distinct. So let's suppose that these ordered pairs are distinct. And our whole goal at this point is to prove f of I1, J1 is not equal to f of I2, J2. If we can prove that, that proves f is injective. Okay, now we're going to divide this up into three cases. Either I1 plus J1 equals I1 plus J2, I1 plus J1 is greater than I2 plus J2, or I1 plus J1 is less than I2 plus J2. Let's start with a case where I1 plus J1 equals I2 plus J2. Now, in the case where this is true, it follows that I1 is not equal to I2. Why? Well, if I1 did equal I2, then you can deduce that J1 is equal to J2. But then that implies the two ordered pairs are equal, which is a contradiction because the ordered pairs are not equal. So yeah, we must have that I1 is not equal to I2. And now, we're ready to show that these two are not equal. And to see how that comes together, check this out. If we apply the formula for function f, we replace everywhere we see an I with I1, everywhere we see a J with J1. Now, since I1 plus J1 is equal to I2 plus J2, we can replace I1 plus J1 with I2 plus J2, I1 plus J1 with I2 plus J2. But since I1 is not equal to I2, we have that this is not equal to itself, where we replace I1 with I2. However, if we apply the formula for function f, this is precisely equal to f of I2, J2. So what we have here is that f of I1, J1 is not equal to f of I2, J2. So that completes case 1. Now let's move on to case 2, where I1 plus J1 is greater than I2 plus J2. And to see that the output values are not equal, check this out. If we consider f of I2, J2, we know that by the first preliminary result, that f of I2, J2 is less than or equal to f of I2 plus J2 minus 1, 1. But then, by our second preliminary result, if we consider the positive integers I2 plus J2 minus 1 and I1 plus J1 minus 1, well, I2 plus J2 minus 1 is less than I1 plus J1 minus 1. So, this statement applies to I2 plus J2 minus 1 and I1 plus J1 minus 1. So really, we have that f of I2 plus J2 minus 1, 1 is less than f of 1, I1 plus J1 minus 1. But then, by our first preliminary result, we have that f of 1, I1 plus J1 minus 1 is less than or equal to f of I1, J1. So what do we have here? Well, f of I2, J2 is strictly less than f of I1, J1. So they're not equal. And that's exactly what we wanted to prove, so this completes case 2. Now we're going to move on to case 3, where I1 plus J1 is less than I2 plus J2. And as you can imagine, we're going to get a really similar situation to what we had in case 2. And to see how it comes together, check this out. If we consider f of I1, J1, well, by our first preliminary result, f of I1, J1 is less than or equal to f of I1 plus J1 minus 1, 1. But then, if we apply our second preliminary result, right, we know that I1 plus J1 minus 1 is strictly less than I2 plus J2 minus 1. Well, applying that to our second preliminary result, we have that f of I1 plus J1 minus 1, comma 1, is strictly less than f of 1, comma I2 plus J2 minus 1. But then, by our first preliminary result, we know that f of 1, comma I2 plus J2 minus 1 is less than or equal to f of I2, comma J2. So what do we have here? Well, f of I1, comma J1 is strictly less than f of I2, comma J2, so they're not equal. So, in all three cases, we have proven that f of I1, comma J1 is not equal to f of I2, comma J2. And this proves that f is injective. And next, we're going to prove that f is surjective. Okay, so what does this mean? Well, it means that for every positive integer n, there is an ordered pair of positive integers I comma j such that f of I comma j is equal to n. So, since we're trying to prove a statement about every positive integer, give me an arbitrary positive integer. I'll call it n. And from here, we want to find an ordered pair of positive integers I comma j such that f of I comma j is equal to n. How do we do that? Well, I will explain the thought process after we prove the following claim. We claim that there exists a positive integer n such that f of 1 comma n is greater than n. Right, and this makes sense because, for instance, if n is equal to 9, then, yeah, there is a positive integer m such that f of 1 comma n is greater than n. Namely, 5, right? Because f of 1 comma 5 is greater than 9. Similarly, if n is equal to 5, then f of 1 comma 4 is greater than 5. Right, and that's the idea. So let's prove this claim. Well, we can show that 2n plus 1 is such a positive integer. If we compute f of 1 comma 2n plus 1 by the formula for f, well, we'll replace everywhere we see an I with a 1, everywhere we see a j with a 2n plus 1. If we simplify the numerator, we're going to get 2n times 2n plus 1. As we can see, the 2's cancel out. If we distribute the n across, we're going to be left with 2n squared plus n plus 1. And since n is a positive integer, it follows that 2n squared plus 1 is positive, so this must be greater than n. So f of 1 comma 2n plus 1 is greater than n. So there is a positive integer m such that f of 1 comma m is greater than n, namely 2n plus 1. So what this means is the set of all positive integers m such that f of 1 comma m is greater than n is non-empty. And I'm actually going to write this set up here. So notice, we have a non-empty subset of the natural numbers. And if you recall, by the well-ordering principle, every non-empty subset of the natural numbers has a smallest element. So, by the well-ordering principle, there is some smallest element of this set. I'm going to call that element t. And we're going to let y equal f of 1 comma t. Now, we're ready to figure out the ordered pair of positive integers I comma j such that f of I comma j is equal to n. And to To see what that ordered pair would be, let's consider, for the sake of argument, that n is equal to 8. Then t is equal to 5 and y is equal to 11. And notice, if we take the difference between 11 and 8, we get 3. In other words, when we take the difference of y and n, we get the j-coordinate of n. And then if we take the difference of t and the j-coordinate, we get the y-coordinate of n. Let's look at another example. Let's say that n is equal to 14. Well, in this case, it follows that t is equal to 6 and y is equal to 16. Now, if we take the difference between 16 and 14, we get 2. In other words, if we take the difference between y and n, we get the j-coordinate of n. And then if we take the difference between t and the j-coordinate, we get the I-coordinate of n. What does this mean? Well, we see that no matter what positive integer n is, the j-coordinate is always y minus n. Then how do we obtain the I-coordinate? Well, we take t and subtract it by the j-coordinate. The claim is that this is the ordered pair of positive integers such that the output value it yields through the function f is equal to n. The claim is that this is the ordered pair that we're looking for. And to show that this is actually the case, there are two things we need to show. First of all, we need to actually show that this is an ordered pair of positive integers, right? Because how do we know that these two quantities are actually positive integers, right? We have to show that. And then after that, we will show that the functional value it yields to the function f is equal to n. Let's start out by showing that these two are positive integers. And let's start out by showing that y minus n is a positive integer. Well, we know that y minus n is an integer, so all we got to do is show that it's positive. Now, we know that y is equal to f of 1 comma t. And since t is the smallest element of s, of course, t is an element of s, which means that f of 1 comma t is greater than n. So, y is greater than n. Subtracting n to the other side, we get that y minus n is positive. So, y minus n is an integer, and y minus n is positive. So, y minus n is a positive integer, as claimed. Okay, but now we want to show that t minus y minus n is a positive integer. All we got to do here is show that t minus y minus n is greater than 0, because we already know it's an integer. And to start this out, we're going to show that t is not equal to 1. So assume for a contradiction, t is equal to 1. What happens if t is equal to 1? Well, we know that n is less than f of 1 comma t. And since t is equal to 1, we can replace t here with 1. And we know that f of 1 comma 1 is equal to 1. So n is less than 1. But n is a positive integer, so this is impossible. Our assumption that t is equal to 1 led us to a contradiction, so we must instead have that t is not equal to 1. Now remember, t is a positive integer, so t is greater than or equal to 1. But we've eliminated the possibility that t is equal to 1, so we must instead have that t is greater than 1. And since t is greater than 1, it follows that t minus 1 is greater than 0. So this implies that t minus 1 is a positive integer. And now that we've shown that t minus 1 is a positive integer, this means that the ordered pair 1 comma t minus 1 is an ordered pair of positive integers. So we can send it into the function f. So t minus 1 is not an element of s. What this means is it is not the case that f of 1 comma t minus 1 is greater than n. we must instead have that f of 1 comma t minus 1 is less than or equal to n. Now, let's perform a computation. If we do y minus f of 1 comma t minus 1, here's what happens. We know that y is equal to f of 1 comma t. And if we write out what f of 1 comma t is, using our formula, well, we're going to replace everywhere you see an I with a 1, everywhere you see a j with a t. And doing the same thing with f of 1 comma t minus 1, we're going to replace everywhere you see an I with a 1, everywhere you see a j with a t minus 1. Now, I'm immediately going to distribute the minus sign across this parentheses. And now, simplifying the numerator here, we're going to get t times t minus 1. Simplifying this one, we're going to get t minus 1 times t minus 2. And the ones cancel out, so overall this is where we're at. Now notice, we can factor out a t minus 1 over 2. And if we do that, for the first term we're going to get t, for the second term we're going to get t minus 2. Right, so just like that. But now notice, in the parentheses, this just simplifies to 2, and this is just equal to t minus 1. So as you can see, y minus f of 1 comma t minus 1 is equal to t minus 1. Now remember, we're still trying to show that t minus y minus n is positive. And we're ready to do that. And to see how this comes together, well, we've just shown that y minus f of 1 comma t minus 1 is equal to t minus 1. But as we wrote before, we know that f of 1 comma t minus 1 is less than or equal to n. Well, since f of 1 comma t minus 1 is less than or equal to n, it follows that the negative of this is greater than or equal to the negative of n. And then, adding y on both sides of this inequality, we have that y minus this is greater than or equal to y minus n. However, y minus f of 1 comma t minus 1 is equal to t minus 1. And now, if we subtract the expression y minus n to the other side and add 1 to the other side, we get t minus y minus n is greater than or equal to 1. Which means we have that t minus y minus n is a positive integer. So, we have proven that t minus y minus n, comma, y minus n is an ordered pair of positive integers. And now we're going to show the functional value of f at this ordered pair is equal to n. And in doing this, we're going to replace everywhere we see an I with t minus y minus n, and everywhere we see a j with y minus n. Now, the first parentheses simplifies down to t minus 1, the second parentheses simplifies down to t minus 2. And over here we have minus y plus t plus n. Now, this entire thing should equal n, so we expect this to equal 0. Now, y is equal to f of 1 comma t. And now let's compute f of 1 comma t using the formula for f. Right? We replace everywhere we see an I with a 1, everywhere we see a j with a t. Next, I'll immediately distribute the minus sign across. And if you simplify the numerator here, you're going to get t times t minus 1. And now let's take this and factor out a t minus 1 over 2. If we do that, for our first term, we're going to get t minus 2. For the second term, we're going to get t. We see that this is just going to simplify down to negative 2. we see that the negative 2 divided by 2 is going to give us a negative 1 times t minus 1. Distributing the minus sign across, we're going to get negative t plus 1. And this just simplifies down to n. So we have computed, right? I like that word, computed, the functional value of this ordered pair through the function f. And we found that it's equal to n. So putting this all together, we gave ourselves an arbitrary positive integer n. And we proved that there exists an ordered pair of positive integers such that if we send that ordered pair of positive integers into the function f, it yields the output value of n. So this proves that f is surjective. So we have proven that f is both injective and surjective, which means f is a bijection from the ordered pairs of positive integers to the positive integers. And so we have found a one-to-one correspondence between these two sets. So there is a one-to-one correspondence between these two sets. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.